Hello, my name is Patrick Parr, and this is my Physics 2212 Lab 3 Magnetic Field of a Bar Magnet. So, for an introduction, the goals of this lab was to measure the effective distance on the magnetic field of a small bar magnet, and we use an observed versus computational data predicted by the use of the Biot-Savart law to compare the distances. And the results was that the magnetic dipole was 3.31 amps per meter squared. Principles. So we have the Biot-Savart law. This relates magnetic field at a point to a tiny current element. And then these are the elements of the law. We have Q, charge of a particle, velocity of a particle, and then the position vector of a particle. We also needed the magnetic field of a dipole, which is the closed circulation of electric current system. And that's shown right here. It varies for being on axis versus on the perpendicular axis. And then we also needed the distance dependence formula, which is the magnitude of the magnetic field as a result of the bar magnet. So here for our observed experiment, the system was the bar magnet, the surroundings were everything else, and the initial conditions were the bar magnet and magnetometer on the phone. So the procedure was we would position the phone so that the magnetometer is perpendicular to the Earth's magnetic field, and then we would pin the magnetometer's location on my phone, or fix the magnetometer's location on my phone, measure the distance between the magnetometer and the bar magnet on and off the axis. So the experimental data for on the axis. So the on-axis distance from the bar magnet to the magnetometer was calculated by using the ruler for multiple magnet field values. The values were linearized by taking the natural log of each side. We then plotted the points and connected them with a line of best fit. Here's our data here, and here is the linear plot. And this is the equation for the line of best fit for our data. And the experimental data off-axis. The off-axis distance from the bar magnet was found by finding the on-axis distance from the bar magnet to the phone, and so the net magnetic field was 100 microteslas. Then the phone was slid in the vertical direction the same distance, and it recorded the net magnetic field at this location. And the y component was found by subtracting the Earth's contribution from the total magnetic field. And so here's our calculations. R is 1 meter, and this is the line of best fit we had from our data. And from this, we were able to calculate K, and then U, or mu in this case, as 3.31 amps per meter squared. And here's our computational model. We just inputted the data that we had from earlier, our perpendicular distance and our magnitudes. And for the computation, this is the results we ended up getting. The most important one is that the theoretical off-axis field is negative 4.135 e to the negative 5 teslas. Possible sources of error. The magnetometer location on my phone could be imprecise, causing an uneven curve and distance results. Other electronic/magnetic objects could impact data, and the magnetic field decreases as the distance increases. This could cause some observations to be inaccurate. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? The results would be less accurate, as the Earth's magnetic field would interact with the reading and skew the results. If you were to stick two identical magnets together end to end and run the experiment again, how would you expect your measurements to differ? The measurements would have doubled, because magnetic field at any location would also double. That concludes my presentation.